Luci. Thank you. We can hear you. You're muted.
Yep, sorry about that. Hi, everyone. So yes, I'm standing in to give this talk about higher order effects in SMEFT for the LHC on behalf of Eleni and also, of course, the rest of the SMEFT Eternal team. So let me go right ahead and get started. Hope you can see my mouse, by the way. So yeah, I mean, obviously EFT is a path to new physics that we're all very keen on pursuing, and therefore the important question that we should ask ourselves, as always, is how we might maximize that reach to new physics of this EFT program. And so, of course, we're using this SMEFT to look for deviations from standard model predictions, and various ingredients go into maximizing this reach. The first is more on the practical side. We want to use as many experimental measurements as possible. And of course, that involves both cross sections and differential rates. And so essentially this counts as improving the global nature of our interpretations. And then on the prediction side, we first, of course, have our, say, baseline theory of the standard model, for which we need to naturally use the best available predictions in terms of QCD and electroweak correction. So by now, the state of the art is, you know, NNLO QCD often, and NNLO electroweak as well. And then the topic of this talk, of course, is that we also want to maximize our precision of the signal predictions as well, so the SMEFT predictions. And so this is what we have been working on for the last few years. So in terms of EFT predictions themselves, in what directions can one go to improve them? Well, the first is, of course, higher orders in the 1 over lambda expansion, the cutoff. And so that involves either, if you're thinking about improving or rather going to higher orders beyond the traditional dimension 6 picture, we have, of course, these squared dimension 6 contributions, but also at the same order, we have things like double insertions of dimension 6 operators, so entering twice in one diagram, which kind of are mixed up with pure dimension 8 contributions, which constitute, of course, an entirely different set of operators, which have only recently started to be worked out and studied in specific cases. So the 1 over lambda expansion is one direction, and then the other direction is in terms of the standard model couplings themselves, so higher orders in QCD and electroweak. And we can do this, as we all know, because the EFT is a well-defined and renormalizable QFT order by order in this 1 over lambda expansion. So any given prediction comes with, you know, an expansion in 1 over lambda, as well as an expansion in the fine structural constants of the gauge theories that we have in the standard model. So why should we bother with these kinds of higher order predictions? Well, there are several reasons, and the first being that, of course, in general, this applies to any higher order calculation. When you start to include loops, you improve the accuracy of your predictions and also the precision. So your central value and your error bars become generally better, or at least more under control. So that's, of course, a generic feature of higher order corrections. And this obviously leads to an improved sensitivity in the sense that you have a more accurate knowledge of the deviations that are predicted by the SMEFT, meaning both at inclusive and differential level, especially, you know, the shapes of your distributions may have non-trivial corrections across the phase space, which will affect your sensitivity when you compare it to the standard model. And also, in terms of the global picture, one may get a better and more precise knowledge of the correlations between the different observables that are predicted by one or more operators in this SMEFT. And these two aspects can be very important in terms of disentangling them from the standard model and to really pinpoint, for example, the origin of a deviation that you observe, or also so pinpointing the new physics origin, and also having a better idea of your reach to the new physics scale itself in the event of observing just the standard model. So that's the first, improved sensitivity. And the second one is slightly more fun, perhaps, in the sense that when you include loops, you also add sensitivity to new operators that can only enter at that level. So you have this loop-induced sensitivity to a bunch of operators that can potentially play an important role in constraining the global picture of the EFT. Wilson coefficient space. So the tool that we have been developing for the last few years and finally put the paper out last August is SMEFT. It's already been mentioned a couple of times in this workshop, and you can find the paper here, and you can also visit the website to take a look at what it's about and what's in there, and of course download it and play with it if you like. So what's in there? We implement the Varsov basis of operators in a slightly reduced parameter space with respect to the 2499 operators by making a few assumptions. So the first is that we assume CP conservation for the moment, as well as a baryon and number and flavor conservation. And then in terms of the large numbers of degrees of freedom that occur, mainly in the flavor sector, so the fermion generation indices, and for example, these 4 fermions and 2 fermion operators, we take an assumption of flavor that singles out the top quark. So this particular one was more or less mentioned by, I think it was Maeve in her talk, as well as perhaps Luca as well. So these flavor assumptions take the baseline universality of flavor symmetry in the standard model, and then break it down. So take these U3s and break a couple of them down to the U2 in order to single out the quark doublet and the right-handed uptype quark. So therefore, the 3rd generation doublet and the right-handed top. And this then means, this then means that you allow basically this class of new operators that singles out the top. So it's top specific or 3rd generation specific, which actually lines up quite nicely with the set of operators that Javi mentioned in his talk before the break, connected to new strongly coupled physics in the top sector. And in terms of the conventions and so on, you can check this note by the LHC top working group. When they introduced the STIM6 top model, we tried to follow those conventions as best we could in order to keep some kind of uniformity in the Monte Carlo tools available for all of us. So here are some examples of what the code can do. We validated these processes, among others. You see that many of your favorite processes are available, such as Strelian, multi-boson production, various numbers of Higgs bosons at loop-induced level, as well as a whole class, of course, of top operators. And all of these predictions, in principle, also include now the class of 4 fermion operators involving at least 2 heavy quarks. So, of course, there's many more things available, given the power of Magra 5 on the square MCA10LO being a kind of general purpose and therefore process-independent tool. Okay, so let me take you through a couple of applications that we present in the paper. So the first thing we looked at was triboson production. So we've heard about that already today, and it's particularly timely, as was mentioned earlier, because it's been recently measured by the CMS collaboration, as well as some evidence has also been reported by Atlas. And so we decided to look at this quark-initiated process here, and QCD corrections to that, involving all the various operators that might enter in both di and triboson production. And so this is the first computation of this process at next leading order in the SMEFT. And this table here, this plot here, shows the K factors for either the order 1/λ² piece or the 1/λ4 piece in these different operators. And the comparison that one should consider is the horizontal lines of a given color correspond to the K factor in the standard model. So each of these colored shapes are different multi-boson production processes, and if the colored point doesn't match up with the line, that means that the K factor is very different from the standard model, and therefore there's some non-trivial information coming in at next leading order. One particular thing that we noticed was this very strange negative and large K factors occurring in this triple gauge boson operator contribution, so-called OW, where at the leading order, this interference contribution is extremely suppressed, and therefore, when you add NLO corrections, the interference somehow gets resurrected, so to speak, and becomes much larger than it was in next to leading order, and actually changes sign completely. So these are very non-trivial effects happening at next to leading order, which is increasing our sensitivity to the triple gauge couplings from triboson production. Another thing that we looked at, was TT bar production. So this is, of course, a canonical process for studying top operators in the SMEFT. And so one thing that we present in this work is kind of a complete survey of all NLO effects in the 4 Fermi operator sector for TT bar production. So all of these numbers correspond to inclusive level results. Of course, differential results are possible as well. And so you see that there's a whole bunch of color octet, TT, QQTT operators, as well as singlets. And this table summarizes, the predictions at leading order as well as next to leading order for both the interference and the square. And of course, at next leading order, the singlets operators don't interfere at all with the QCD amplitude, and so these numbers correspond to the interference at one, which is a pure loop effect in the SMEFT. And then the numbers in brackets here, of course, arise and refer to the interference of these singlet operators with the electroweak mediated process of Z's and photons, which turn out to be sort of similar in magnitude to the loop-induced QCD effects from these singlet operators. So in this case, they're all rather mild, and so you're likely to be quite dominated by the quadratic effects until the sensitivity improves significantly. Another thing that we did, apart from computing 4 top production at next leading order, which I don't show the results for, but you can take a look at the paper, and it's related to, of course, the talk by Javi earlier, is to look at loop-induced sensitivity coming from the same operators that affect 4 top production, so these 4 heavy operators, but entering in TT bar. So these operators mediate interactions with either 4 tops or 2 Bs and 2 tops. So we compute for the first time this loop-induced sensitivity. So you have either a gluon-induced piece, which is finite, or a QQ bar-induced piece, which can be interpreted as a mixing with the corresponding heavy light 4 fermion operator, as was discussed by Javi in the context of E plus E minus to TT bar operators, where only this type of contribution is present, of course, for the lepton colliders, so with the E plus E minus in the initial state. And so we compute all these numbers and find generally that things go more or less as expected, in the sense that you have loop suppressed effects, so the numbers are a bit smaller, but of course it's known that these operators are not so well constrained by these processes yet, because they're quite statistically limited at the LHC. And we noticed one particularly interesting number here, which for this singlet operator, which turns out to be at the inclusive level of a similar magnitude to the tree level QQTT operator. So we're very intrigued by this particular combination. And this operator also happened to be the one that doesn't interfere very well at tree level in the 4 top process as well. So there's some potential complementarity there, which we try to dig into by looking at some differential level plots. And you see that there's some non-trivial shapes going on here for the different interference contributions. And this guy turns out to be the largest one here. It's divided by 10. But you see that the standard model here is divided by 1,000. So you're really talking about needing quite some high precision at near the threshold for this to be complementary to the existing probes for these operators. And finally, the last thing we looked at were loop-induced processes, just to kind of showcase the capabilities of the model. We looked at multi-Higgs production, in particular triple Higgs production from gluon fusion, which was a new calculation, and it depends similarly to the single and double Higgs production, particularly double Higgs production, on a class of operators like this, CH, the top Yukawa, self-coupling, chromodipole, and contact glue Higgs term. And so these radar plots are supposed to summarize the various relative sensitivities compared to the standard model, either from the linear term or the quadratic piece, from the different operators here along the circle for either single, double, or triple Higgs production. In some cases, we do note that triple Higgs has a stronger relative sensitivity in almost all cases. However, oh, by the way, this is for 100 TV collider, because of course, triple Higgs is academic for the LHC, and indeed has a very much suppressed cross-section in the standard model. So I think it would be an interesting process in particular to use as some kind of cross-check, given the fact that we might observe, if we observe a deviation in double Higgs in the future. And then finally, loop. So all of this sensitivity, we need to exploit it in global fits, and you can see how different Higgs production processes. This is a diagram by Luca Vantani. Lots of different loops can enter and give you sensitivity to all kinds of couplings. And so what's interesting is to look at fits. And so here's just showing some plots from some results that Luca already discussed yesterday, where you can combine then top and Higgs data and diboson data to obtain bounds, including some of these loop effects. And one thing that the last thing that Eleni wanted to show was this Fisher information table, which is somewhat preliminary. I hope it's not outdated already, which looks at all the different operators and splits up the information content with regards to the sensitivity from the fit, coming from different sectors, so TT bar, TTV, and so on. And so you see, for example, that for some of the operators like the top Yukawa and the chromodipole, the information content is quite nicely split, particularly for the dipole from TT bar production for the dipole, but also quite significant information coming from the Higgs measurements, which arise purely from this one loop effect. And the top Yukawa sensitivity is actually dominated by Higgs measurements rather than TTH at the moment. And perhaps even more interestingly, a lot of these top electroweak couplings actually derive much of their sensitivity from Higgs decays. So not only can they enter at tree level from, say, TTZ production, but they can actually enter also at one loop level in Higgs decays to gamma gamma and gamma Z. And so these computations were included in this SMEFT analysis, and it turns out that there's really some non-trivial stuff going on here, and highlights the importance of including these operators in these predictions for interpreting Higgs data. And then finally, I think you see some of these likelihood posterior distribution plots from this SMEFT analysis as well, where again in blue you have the leading order posterior, and in orange you have the inner lobe posterior. And you can see how in many cases one has a significant effects in the interpretation of a global LHC and more data analysis on this very large SMEFT parameter space. So let me conclude there. I hope I didn't go too much over time. So the SMEFT and alert tool is finally released. That means that fully automated one-loop contributions, including next leading order and parton shower and loop-induced effects, are now available for the masses, so to speak, and meaning that now we can use these results in global fits and dedicated studies. In terms of planned extensions, we hope to increase the flavor structure soon, and especially include light 4 fermion operators and go beyond CP conservation, and of course are always open to requests and suggestions from outside. So thanks for your time.
Thank you, Ken, very much. This nice talk. Are there any questions from the room first?
I don't see any. There's one.
Hello, I have a question. Can you hear me?
Yes.
In the 16th page, I just wonder whether there exists a logic correlation among CPT, C1, C1Q, C1UT, C8QU, because I found there exists a very large difference between leading order and the next leading order bounce on CPT and the C1. C1. Let's see.
This one here. This one here.
C1 UT and C8QU.
C1 UT. Okay, here. Yes.
In the right figure.
Okay, we hear you well now. Good.
Right. So yes. So you're saying that there's a big difference between leading order and next leading order in these plots here, in these limits. And so is there a large correlation? That's quite probable, yes, because these are too heavy, too light operators entering in top pair production, as well as any kind of TTX process. And so it seems here that, of course, it's better probably if one of the SMEFT authors comments, but I think somehow, yes, there's some large corrections occurring at NLO, and certainly it's true that these operators will be correlated also with actually all of the other QQTT operators in principle. Now this one is mainly bounded, if I remember correctly, this is a right-handed top coupling with the Z, which already Javi mentioned as well. And so this one, I believe, if I look at this previous table, is most strongly bounded by TTZ and a little bit from the Higgs decays as well. So there's kind of a nice interplay there going on. So I don't. It may be correlated with the others via TTV production, where all of these 4 fermion operators also enter. But maybe SMEFT authors can say more about this effect of next leading order.
Okay, thanks.
I don't see any other question here.
Anybody online? I mean, maybe something I can comment on also is that as future prospect, one could also compute those 4-top induced contribution to E plus E minus to TT bar that was also mentioned in Javi's talk. So going beyond RG mixing that was used in their work to also compute the finite contribution from the loop and yeah, feed in that kind of analysis. That's something we also plan to do in the midterm.
Yeah, I think that's definitely an interesting thing where, of course, Javi argued that in the strong coupling limit, the RG effects dominate, but perhaps in a more general case, one may want to check the effect of these finite contributions. And I think in some cases, that's something that SMEFT will be able to do. Yeah.
Okay. There is no more questions. Maybe we can thank Ken again.
Thanks to Eleni for preparing the slides as well.
Indeed, it's too bad that she couldn't make it this very last minute. Thank you, Ken. And
Sure.
we're switching gears a little bit, moving to on-shell amplitude application for effective field theory. First with Alex Pomerol. Alex, can you unmute and try to share your screen? Hi, can see you.
Hello.
We can hear you too.